the velocity, angular velocity. Yes.
Close, really close, philosophically different.
2 pi frequency, 2 pi f.
Okay, it is 2 pi f.
Yes, 2 pi f.
What is 2 pi f equal to? Not angular velocity or angular speed. I will say from a practical point of view, you're right, but from a philosophical point of view, you're close.
Rotational spin? No.
No, that'd be the same as angular speed.
Yeah. Angular frequency.
Yes, angular frequency, omega. It is the same symbol as angular speed, but this is angular frequency. Now, what is printed on the tuning fork is the regular frequency, the number of hertz. And so we can now find, based upon this, the frequency should be omega divided by 2 pi, which is experimentally 2008.2 divided by 2 pi. And we better get something somewhere around 340, or is it 320? Somewhere around 320.
Yeah, 319.6 hertz.
All right. And then a third way is beats, and this can be a little bit tougher because this is not incredibly loud, but let's see if we can, how well we can do this. Can you all hear that?
Yes, I think.
Okay.
Maybe not.
Yeah, not really. It's too far away from me.
Okay, then this will be for you two, or you can move closer, Holden, if you need to. We'll definitely have to turn this down though.
Is it going?
It is now, but it's fading a lot. All right, so that's from the speaker.
Kind of hard.
All right, let's see if we can get the beats at 319 here. All right, so that's 319.
I heard it. I heard it once.
You can hear the beats?
I heard one beat. I didn't hear it that time. Seems like the speakers in that has a different pitch, like it's.
Well, in theory, that would work. However, apparently in practice, that's a horrible way of doing it. Now, I would trust the 319.6 slightly more than the 320 from a quality control point of view. That we're not; these things are mass manufactured, and so they probably have there's a tolerance to it. But this is not a high precision piece of instrument. Piece of equipment, because we're not doing it. If we were doing a multi-million-dollar experiment with this, then yeah, you better be sure that that's going to be 320 out of several decimal places.
Did they, why, they didn't put a plus, yeah, I didn't see a plus or minus and decimal point.
Yeah, I mean, it's I think if you went to the specs for the manufacturer, I suspect that it would be there.
Yeah, I'm kind of surprised they don't do something like that, similar to what they do with resistors.
Oh, with the color coding?
Yeah,
Yeah, for whatever reason, they just don't. The paint would affect, you'd have to put it on the handle, which is where you're holding it, and so that potentially could,
Rub off.
yeah, eventually rub off.
Yeah.
You rarely hold resistors on a regular basis by the side. You hold it long enough in order to put it into place, and then you take your hands off.
Yeah, or maybe hold it by the leads with pliers. Well, actually that might not be the best idea.
We never actually did the second number in the parentheses there, the phase shift.
Oh, yes, thank you very much. And that's because we're doing a cosine curve. Cosine curves start at the top and then move down, so when time is 0, that's where a cosine typically starts. But because it's reality, this thing is vibrating 320 times a second, the odds that we would actually hit that perfectly at the maximum pressure weigh against it. And so this is the shift in radians of how far off we are. All right, so as I vibrate this, and I put it over here, this thing is vibrating back and forth. The tines are vibrating back and forth, pushing air down and then sucking air back. So we get this compression rarefaction. Comes down, the water hits the scummy surface of the water here and then reflects. It is a fixed in, and so the theory, the wave will invert when it hits, and you'll get some constructive and destructive interference. So the simplest wave looks like that. So we have an antinode at the top. Antinode is what you're going to hear the loudest because you get the maximum vibration there. And we have a node down here. So node, antinode. And this was covered relatively quickly near the end of class last Wednesday. How many waves is that?
Half.
Not a half.
1/4.
Yeah, quarter.
Yeah.
So the wavelength is 4 times the length being from the top of the tube here to the surface of the water. The speed of sound, we'll assume that the temperature is still close enough to the same. So that is 340.
3.8.
Meters per second. And that's equal to the frequency times the wavelength. So the frequency I should be, again, well, the speed divided by the wavelength. So 343.8. Oh, sorry. Try that again. What I was writing down was not incorrect, it's just not what we're looking for here. Ultimately, we want to find what is L. So the wavelength that is produced by this tuning fork is the speed divided by the frequency. So 343.8 divided by, let's go with the 319.6. So this is meters per second, and this is hertz.
So 1.08.
Yeah, that's pretty much what I got.
Units?
What's units?
Meter per
Meters per second.
Yeah.
Not meter per second.
Meters.
What'd you say?
Meters?
It's just meters. It's a wavelength, it's a length.
Oh.
From a unit point of view, remember hertz is a 1 over a second. So it's a meter per second divided by a hertz, which is a meter per second divided by 1 over seconds, which is a meter per second times seconds over 1
Cancel out.
over meters. So I would expect to hear it loudest when the length of the air column is 1/4 of the wavelength. So the length of the air column should be 1/4 times 1.08 meters.
Uh, 0.26. Yeah, that's what I got. Even though it's a 260 to the -3rd.
Okay.
Because I'm gonna switch this thing
It's not 0.27?
Yeah, I got 0.27.
to, I got 0.26.
Did you 1.08?
Oh, whoops, I put what? Oh, I me to.
All right, so I would expect it to be the loudest when the air column is 0.27 meters or 27 centimeters. Now, for some reason, I haven't quite figured out why they did it, but they were consistent at least, is that 0 here is actually 2 centimeters from the top. Now, I thought it had something to do with some dealing with the width of it, because you can potentially get some resonances happening across this way as well as this way, and it's to offset that, but the more research I've done, the more I'm confused about why they did it. What would make sense is I would call the company, but I haven't done that. So I would expect that since 27 centimeters, so on here, I got those 2 centimeters plus 25, so I'm expecting that to be the first time we hear it loudest is somewhere when the water column is here. So we need to set that up. And, there's one.
Look for Joel.
The tuning fork holder.
Oh.
And we're at 320. Now I found, just from having done this experiment enough, it tends to work best if the tines are like this, because the tines are going to be vibrating back and forth like this, and so it's best if they're oriented that way over the tube. Is that enough? Nope. There we go. And so I'm going to bring this down. There's some exciting video right there. Everything went black. And Holden, you now have an alibi for this time period.
Yeah, that thing needs to be cleaned.
Yep. All right. So I'm going to raise and lower the water just by moving this, so we'll get that horrible screeching noise. And that was a resonance right there. Turn that around. So where it's loudest, sort of note where that falls on here.
Heard that.
Yeah, I
24, it looks like.
All right, so we're off a centimeter. So we got a 4% error there. Where's the next resonance? How high does the water column need to be for the next bit? Well, we can make our prediction. And everything went black again. Remember, you had to add a half wave every single time. So the next simplest, because I have to have an anti-node at the free end and a node at the fixed end. Something like that. I'm sure your notes you will draw perfectly. So how many wavelengths is that?
Growing fall.
Yep. Because we add a half, we have to start with a quarter, we add a half, and so we end up with 3/4. This is the third harmonic. Second harmonic does not exist. unless that's the phantom resonance that we get there. So I would expect, my wavelength isn't changing because the speed of sound, we're assuming, is still the same, and the frequency of the tuning fork is still the same.
I got 0.81.
So we'd expect when the length is 0.81.
Yeah, I just did 0.75 times 1.08 to get,
You did 0.75 times 1.08. Oh, yeah.
yeah,
Or you could just do 3 times that.
yeah, that's,
So again, offsetting for that 2 centimeters, I expect it to be at the 79 centimeter mark, around here. It will not be as loud as here because it is vibrating against the sides more, because it's got longer to go. And so I would expect that you'll lose some of the energy there. Now it is helpful to two things on this. One, as we lower the water level, at some point the reservoir might fill up. So it's good to have something nearby to dump the water into very quickly if we need to. The other bit is we probably should get it closer before we actually do it. If we were actually doing it at an experiment instead of demonstration, I would recommend getting it down there first. Now, ideally, you should not, in an experiment, you shouldn't go, oh, this is the number I'm expecting, so hey, let's make sure we get down there so we get that number. This is the one lab where if you don't do that, you can really mess up your results. Let's see if I can get the false harmonic. So as it drops, there was 1 point.
what's false harmonic again?
Sometimes you hear, it sounds like it gets a little bit louder, and then it softens again, and then it gets really loud at where we were expecting it to be.
Oh,
Wasn't hearing it there, so maybe we'll hit it on the way down, or maybe this is just the wrong tuning fork we're showing now. It is a demonstration, so what are the expectations? It'll work exactly the way you expect.